in section 6.5, and we're going to talk about the trigonometric form, and I'm just going to write trig for short. Trig form of complex numbers. And it may seem strange to suddenly switch from talking about vectors to talking about complex numbers, but we'll make the connection between the two, and it hopefully won't seem so strange. So quickly, to remind us, when we're talking about a complex number, just like we kind of usually use the variable x or y when we're talking about algebra, when we're talking about complex numbers, we usually call our variable z. So I'm going to say z equals a plus bi. So z is a complex number, a plus bi. When we write a complex number, a and b are real numbers, and I is the square root of -1, and that means that I squared equals -1. So that's what we're talking about when we're talking about a complex number. Well, the connection that we're going to make between complex numbers and vectors is we're going to put these complex numbers on what we call the complex plane. So I'm going to draw a set of axes. And rather than the x and y axis, in the complex plane we're going to call this the real axis, and this the imaginary axis. And when we do this, z equals a plus bi, we can think of this as a point in the complex plane. So we call this the complex plane. So what we think about is going over by a units and up by b units. So this is z equals a plus bi. And if I project this down and project this over, that side, that length is a, and that length is b. Sorry, did it backwards. This is b, and this is a. We're going over a units, and we're going up b units. So we can think of this complex number, a plus bi, as this point in the complex plane. I go over a on the real axis, I go up b on the imaginary axis. And this will give us several benefits. Several nice things come out of thinking of complex numbers this way. So we have our complex plane. We can plot our complex numbers on the complex plane. We call the absolute value absolute value of z, and we say z is let me say one other thing before we write our equation. Absolute value of z, this is the distance from the point 0, 0 from the origin to our point in the complex plane. So we're talking about this distance. The length of this segment is the absolute value of z. And the way we come up with the absolute value of z should be familiar by now. Square root of a squared plus b squared. So it's just the length of the hypotenuse of this right triangle. So we call that the absolute value of our complex number. And we're going to do something else with that absolute value in just a second. So, any questions on what we mean when we're talking about the complex plane and absolute value of a complex number? We're talking about this length. The distance from the origin to our point is the absolute value. Let's do a quick, easy example. So let's say we had z equals 4 minus 3i. And we want to find the absolute value of z. So this one we should be able to do without even going to our calculator. What's going to be the absolute value of that? 5. So this is a 3, 4, 5 triangle. So this would be 4 units here, and we go down 3 units. So our hypotenuse would be 5. And if we were, just as a quick reminder, this is the square root of 4 squared plus 3 squared. So that's how we find the absolute value of a complex number. Now, hopefully, when we drew this up here and we had this plane, hopefully that got a few of us thinking about the way we talked about vectors, because this is really the same way that we talked about vectors and a point in the plane, and we talked about a line segment. So what we want to do is make a connection between complex numbers and the way we talked about vectors, and that's gonna give us a nice little tool. So let's redraw this drawing, and now I'm going to include an angle here. So here's our imaginary axis and the real axis. And I'm going to plot this point z equals a plus bi up here. And I'm going to draw this length here. And we're going to talk about this angle from the positive x-axis in standard position, just like we did when we talked about trigonometry, just like we did when we talked about vectors. We're going to call that angle theta. So if I do this side is A, this side is B, and we're going to call this R for radius. And our radius is the absolute value of z. And if we label our triangle like this, we can say A equals, how would we find this side of the triangle if we know R and we know theta? Cosine. So it's going to be A equals R cosine theta. B equals R sine theta. So we could write this complex number as z equals R cosine theta plus I times R sine theta. And I can factor out that R is common to both of these. So z equals R cosine theta, or R times cosine theta, plus I sine theta. So we can represent this number in terms of its absolute value and this angle from the positive real axis. We call this the trigonometric form of a complex number. And I'm going to write the trig for short. And we give R and theta some special names here. We call R is the modulus So R is the modulus of Z, and we call theta the argument of Z. So we write our complex number in terms of the modulus and in terms of the argument. Now what I want to do, we'll do some conversions in just a second, and then we'll talk about how we apply this way of thinking about complex numbers. Now one reason, what we'll do today is we'll show why this is helpful in some cases. But one reason that we look for things like this, where we can connect complex numbers and vectors, we can connect complex numbers and trigonometry, is because any time that there are in math and in lots of things, when there are connections between things that seem totally separate, that's a hint that there's more going on kind of beneath the surface. I think of it as little islands in the ocean. You see the little island, but you get down below the surface and there's more to it, and you go down deep enough and those little things are actually connected and they're part of one big thing.
Hi,
Yes.
is Tim Morton in this class?
Yes, he is.
Can I borrow him for you? Let's go quick.
Sure. So when we can make these connections, there's a hint that there's something bigger going on beneath the surface. And what this eventually allows us to do, we can connect complex numbers, we can connect trigonometry, and if you go further in math, eventually you connect trigonometry, complex numbers, and exponential functions, and they're all kind of mixed together. And it's a really cool thing. So that's one reason that we do it. The other reason we do it is because thinking of complex numbers in trig form simplifies a lot of operations, and that's what we're going to talk about in just a second. But really, it's a hint when you see these connections. It's a hint that there's something bigger going on beneath the surface, and if you can figure out that bigger thing, you get to something really interesting. All right, so we have this trig form of a complex number. This is exactly like we talked about vectors. We can think of this complex number like we thought of a vector. This angle, just like we thought of the angles with the vectors. We know that R, we found R, so R, our modulus, is the square root of a squared plus b squared. And to find our argument, theta, how are we going to find our angle theta if we have our complex number? What did we do when we had our vector, when we had AI plus bj? Inverse tangent. Theta equals the inverse tangent of b over a. So we can find our modulus from the real part and the imaginary part. We can find our argument from the imaginary part and the real part. And just like we did with vectors, the only thing that we have to be careful with when we use our calculator to find the inverse tangent is making sure that we're in the correct quadrant based on the signs, positive or negative, on A and the B. We just have to get our angle in the correct quadrant. All right, so let's look at a couple of examples. We'll go both directions with our conversion, from A plus BI form to trig form, and from trig form to A plus BI form. And then we'll talk about how this trig form of a complex number simplifies some operations. So here's our example. We want to write z equals negative 2 plus 2i in trig form. So to write in our trig form, we need two things. We need r, we need our modulus, and we need theta. So our modulus, how do we find our modulus? Get us started, square root. A squared plus b squared, so that's going to be 4 plus 4, square root of 8, and how can I rewrite square root of 8? 2 root 2. And theta is going to be the inverse tangent of 2 over negative 2, or the inverse tangent of negative 1. And what quadrant do we want our angle in? Second. We want it in the second quadrant, since our real part is negative and our imaginary part is positive. So that puts us over here and up here. So we're over here in the second quadrant. So we want a second quadrant angle. So in the second quadrant, what angle has an inverse tangent of negative 1? So it's 45 degrees from, there we go, 135. And usually in trig form we use radians, not always. So we could say theta equals 135 degrees, or in radians, 3 pi over 4. So, yeah, Daisy.
So, could you know that just from knowing it, where it should have been plotted, like knowing
Yeah.
it might be the second quadrant,
Yeah.
and actively finding out r?
Sure,
And
so-
the square root is 2 square root 2, and then with that, so it is 45, and you just know that happened throughout data? Or
Um,
throughout data?
Well, so, well here, if what you're asking is, we could see that this,
Yeah,
like the
that-
slope of that line is
Well,
negative 1,
wait,
and that's a 45 degree angle, you could do it that way. But 2 square root of 2,
Okay.
so any complex number that would be on that line
okay, so that
would have an argument, an angle of 3 pi over 4. Does that?
Yeah.
Okay, good. So to write this in trig form, we would say z equals 2 square root 2 times the cosine of 3 pi over 4 plus I times the sine 3 pi over 4. And that would be our answer. That would be this complex number in trig form.
What's the benefit of having trig form?
We'll talk about that in just a second. So keep that in mind, and we'll talk about that in just a second. All right, questions on that example? So part of what we're doing here, just is the practice of conversion, and also visualizing where these points are in the complex plane. The benefit is going to come in just a second. So let's go the other way now. So we want to write, let me find my 4 cosine 5 pi over 6 plus I sine 5 pi over 6 in a plus bi form. A plus bi form, you might hear it called standard form. You might hear it called rectangular form. So just when you see those two other names, I think our book always calls it a plus bi form. So we just want to do this conversion. So for cosine of 5 pi over 6 is what? Square root of 3 over 2? Positive or negative? Negative. Sine of 5 pi over 6? 1/2. Now we're going to distribute, so we get negative 2 square root 3 plus 2i. So this would be our answer in a plus bi form, in standard form, in rectangular form. So that's just going back and forth. Questions there? This is pretty easy. Kind of mechanical. So let's talk about where using our complex numbers in trig form helps us out. Multiplication and division. So think back to how we had to multiply and how we had to divide complex numbers when we had them in a plus bi form. We had to FOIL, we had to combine like terms. Remember that I squared was -1. If we wanted to divide, do you remember how we divided complex numbers? Multiply the numerator denominator by conjugate of the denominator, and then do all that simplification. Lots of work. So what I want to do is go through this process, and hopefully you'll see something familiar at the end. I'm going to write two complex numbers in trig form, and we're going to do the multiplication. So I'm going to say Z1 equals R1 times cosine theta 1 plus I sine theta 1. And Z2 equals R2 cosine theta 2 plus I sine theta 2. And we're going to multiply these two together. Z1 times Z2. So we get this I've got my plus sign here, plus I sine theta 2. Well, R1 and R2 are just real numbers, so I'm going to multiply those together. So I get R1 times R2, and then these two parentheses, I'm going to FOIL those out. I'm going to distribute everything and FOIL those out. So I'm going to multiply, so my first, I get cosine theta 1, cosine theta 2. My outside, this times this, I get plus I times cosine theta 1 sine theta 2. Inside, I get, so these two, and I'm going to write the cosines first, cosine theta 2 sine theta 1. And then the last, I squared is -1, so I get a minus sine theta 1 sine theta 2. So that's a lot of stuff. Now I'm going to combine the parts with the i's and combine, so I'm going to combine the imaginary parts and combine the real parts. So I get R1, R2, cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2 plus I times cosine theta 1 sine theta 2 plus cosine theta 2 sine theta 1. And then I need one more. There we go. Now, I want you to look at this quantity and this quantity. And hopefully, those look somewhat familiar. Anybody recognize this? Not quite. You're on the right track though. This is the addition formula. Very nice. So this is the sub formula for the cosine. This is cosine. Very nice. Theta 1 plus theta 2 plus I times the sine theta 1 plus theta 2. To multiply two complex numbers in trig form, and this is z1 times z2, we multiply the moduli and we add the arguments. So if we have two complex numbers in trig form, all we have to do is multiply the r's, add their angles. We don't have to FOIL, we don't have to distribute, we don't have to remember that I squared equals -1. Multiply the moduli, add the angles. Really, really easy. Yes? Here?
Yeah.
This whole thing simplifies to this. This whole thing simplifies to that. This cosine theta 1 sine theta 2 cosine plus cosine theta 2 sine theta 1 is the sine of theta 1 plus theta 2. So that all simplified down to that. The same thing here. And we're not going to go through the whole process, but z1 divided by z2, if to multiply we multiply the moduli and add the angles, what are you going to guess happens when we divide? Divide the moduli, R1 divided by R2, and we subtract the angles. So divide and subtract. This is way easier than multiplying the numerator and denominator by conjugate. Multiplying out, simplifying, combining like terms, canceling when we can. All of that stuff that we had to do when we had our complex number in standard form, way easier. Divide two numbers and subtract two angles, and we're done. And then if we wanted to convert back, do the multiplication or division first in trig form, and then convert back to standard form, to a plus bi form. Way easier. And then tomorrow, what we're going to talk about is using trig form to find powers and roots of complex numbers. And if you think about how complicated finding something like 2 plus 3i to the 7th power would be, using a plus bi form. Multiplying all of that stuff out would be really complicated. Using trig form, really, really, really easy. And we'll be able to find roots, 7th roots, 6th roots, 10th roots of complex numbers very easily using trig form. So let's do a couple of examples of let's do an example of multiplication, an example of division, just to see how easy it is. That's really all I'm going to talk about today. I'll mention a couple of things right at the end, but then we'll have plenty of time to work. You should be able to finish everything you have. Okay, so pretty easy idea. And then tomorrow we'll get into some more interesting stuff. So, I just wanted to mention, we come up with this formula by doing the same thing that we did up here. We would multiply the numerator and denominator by the conjugate of the denominator and go through all the process of multiplying and simplifying, and we would come up with this formula. All right, so let's look at an example of multiplication, example of division. Z1 equals 8 cosine 120 plus I sine of 120 degrees. And Z2 equals 6 cosine of 150 plus I sine of 150. And I just want to mention really quickly, the examples we did here, they all have nice unit circle angles. Your points in the complex plane don't necessarily have to have nice unit circle angles. You could end up with something where you had to do it in your calculator, and your angle could be 23.78 degrees, or you'd have to find the sine and the cosine of 47.69. So your angles don't always turn out to be nice unit circle angles. That's just what we use for our example. So let's do Z1 times Z2. So we're going to multiply the moduli. That's going to be 8 times 6 times the cosine of, we're going to add our arguments, cosine of 270 plus I sine of 270. We just added our angles. And if we want to write this in a plus bi form, this is going to be 48 times the cosine of 270 is 0. And the sine of 270, negative 1, minus I. So this would be 48, negative 48I. And if I plotted that point on the complex plane, it would be down here on the negative imaginary axis. Multiplication, so easy using this. Z1 divided by Z2. Divide the moduli. Subtract the angles. 120 minus 50 is negative 30 degrees, and then plus I times the sine, negative 30 degrees, and we can write that. So this would be we could reduce this. This would be our trig form. If we want to write it in a plus bi form, we would get 4/3. The cosine of negative 30 square root of 3 over 2. And the sine of negative 30, negative 1/2. And we could write this out, so we get 2 square root 3 over 3 minus 2/3 I. and that would be our complex number in a plus bi form. This would be our trig form. This would be a plus bi form. So multiplying numbers when we have our complex numbers in trig form, very, very easy. Tomorrow we'll talk about how we find powers and roots of complex numbers when we use trig form. And where this leads, eventually one place that this leads, is it turns out that there's a connection between complex numbers, trigonometry, and exponential functions. And when you start combining all of those, you get a very, very, very powerful tool that shows up very often in science and engineering. And it's also just a really, really cool idea that all of these things that seem so separate turn out to be connected. And if you get a chance, when I was an undergraduate, one of the most interesting math classes that I ever took was called complex variables or complex analysis. So when you're in college, if you ever get a chance to take a class and you're not sure what to take, and you're interested in a math class, complex variables, complex analysis is really a really fascinating part of mathematics. Really different way of thinking. Brings all kinds of different ideas together, mixes them together in ways that you wouldn't imagine at first. So that would be, if you ever get a chance, I would recommend that. And I also wanted to mention before we stop today that we started by making a connection between complex numbers and vectors. What we did with multiplication and division doesn't carry over between the vectors and complex numbers don't share that piece because we didn't multiply two vectors straight times each other. We don't divide two vectors one by the other. We do some different kinds of operations. So that's where they're different. So we kind of use that idea of thinking of a complex number as a vector to get us started, and then we went a little different direction with that. So don't think that complex numbers and vectors are exactly the same thing. They're similar in some ways. All right, questions? All right, homework. EOE, every other even. All right, there you go.